Well, hello everybody. We are going to talk about Newton's method, and Newton's method is a technique for approximating zeros of a function when we are trying to find out where and basically is going to use tangent lines to approximate what's going on to find the x-intercepts. All right. This is remember when we talked about finding zeros when we were trying to find functions, and this beginning part right here should sound very familiar. If we have a function that is continuous on a closed interval and differentiable between a and b, if f of a and f of b change signs, then this is the intermediate value theorem. And basically, what happens here is, remember we were talking about the intermediate value theorem, that in the intermediate value theorem, that if you get f of a is positive and f of b is negative, and you find out those two values, well, you'd have to do some more work to find out where it crosses the x-axis. Well, this is a way of finding where it can happen. And so what we're going to use is we're going to use a tangent line, and basically what you have to do is you have to make an initial guess, and we're going to call that x sub 1. And so if we're basically going to pick a point like x sub 1, and when we substitute it into the function, we'll have f of x sub 1. All right, and that would be our point where we're going to cross. So the equation, we're going to use the tangent line equation to help us find this, and this is very much like what we're going to do in 3.9 when we get there. But this, we're going to say, okay, y of f of x sub 1, so our y value minus, basically I'm using point slope here, and so we will basically go through and take this equation and solve it for x, and then that will give us the equation that we'll use over and over again. And that equation that we're going to get, the equation that we're going to get out of this, will be the place where where our tangent line approximation crosses the x-axis. And so I'll show you what that means in just a second when we get to, I have some graphs that I can show you. So let's go through. If we set y equal to 0, so I'm going to take this equation and set y equal to 0, and then everything else after I set y equal to 0, I'm just going to do some algebra here to simplify this and get the equation solved for x, basically. So first thing I might do is distribute my f prime of x sub 1 and get rid of this 0, so we'll kind of do that all in one step. I'm going to distribute my f prime of x sub 1, so I'm going to get x times f prime of x sub 1 minus x sub 1 of f prime of x sub 1, and then a little algebraic maneuvering because I want to get my x value to be by itself. I'm going to add this part across the equal sign, move it over there. So x sub 1 f prime of x sub 1 will equal minus f of x sub 1, because I moved this guy across the equal sign, I added it over there, and that will be equal to x of f prime of x sub 1. So then I want x to stand alone, so I divide everybody by x sub 1, and so these guys being divided by f prime of x sub 1, over here, these will reduce out because they're 1. Over here, it'll be left with f of x sub 1 divided by f prime of x sub 1. So this whole equation, when I start with some initial x value, is going to give me that I end up with x sub 1, that's from this part right over here when I divide those two, minus what's left over, this part of the fraction, my y value at x sub 1 divided by the slope at x sub 1. All right, and so this is the equation right here that we are going to use to help us find what's going on here. And actually, this isn't x sub 0. This is actually x sub 2. It gets us the next value above where we're at. All right, so if I was starting with x sub 1, then this is going to be x sub 2. If I would have started with x, it would have been x sub 1 over here. And so over here, when I write this, so if I want to start with x sub 2, if I want to find x sub 2, this is what we just did, x sub 1 minus f of x sub 1 f prime of x sub 1. And so then if I'm going to go through and do this for x sub 3, well, I could go through and do the whole algebra of solving it again, but I'm hoping that you can see how I'm getting this equation, that I am getting another value here. Now, what does this all mean? Well, let's look down here. If I want to find out where this 0 is on this graph, Each time I go through these become, this gives me an approximation. So what I have here is I pick some x sub 1 value, say x sub 1 over here, and I follow it up, and I draw a tangent line, and all that work that I did up there, that line that I had drawn, was to get the tangent line approximation of what's going on at this particular point. So there's approximately the point, and I draw a tangent line here, and that tangent line goes down and crosses the x-axis. And so what this equation does, if this top equation up here on this one, will kick out the x value right here of x sub 2. All right, so this work right here at the top cuts out this x sub 2, which gets me a little closer. So then I take the x sub 2 value, which would be right here, x sub 2, and carry it down, and then draw a tangent line to that. Because if you notice that when I draw this tangent line, this is my y value down here. Oops, I'm erasing, sorry. This is my y value down here. That's my f of x sub 2. And if I draw a tangent line to that, you can see that the tangent line at that point will then cross again over here somewhere. Will cross again on the other side of the x-axis, or the other side of it, and that would give me my x sub 3. But you can see that I'm getting closer each time. So then I have this x sub 3 that's really close, and if I keep going with this over and over and over again, yeah, I'd get an x sub 3, and then I'd draw another tangent line there at my y value, and then that tangent line will be ever closer. And if I continue to do this over and over and over again, I'm basically going to end up with a value that this x sub 4 might be really darn close to what's going on here. And so that's what these guys are doing. These are calculating the x-intercepts that where I'm crossing the x-axis, so that I could find, get ever closer to this value that I want, the x-intercept value that I'm looking for. Okay, so when we're doing this, we have to make an initial guess, and that guess is on you. You pick some value in x sub that's close to where it crosses, and then you start working your way closer and closer. This equation is the equation that we got just a few minutes ago. And then this equation, step 3, is if there's a desired accuracy that you would want for this, then you would take the absolute value of the previous term minus the new term, and then that'll, when you subtract those and take the absolute value of them, you would end up with some accuracy, like a percentage that you're going to be close to, or a decimal that you're close to it. And so we will practice that in just a matter of moments here. So here's my first example for you. We're going to find out where f of x squared minus 2. Now this one, ideally, if I did this one, the ideal situation for these guys is ones that we can't calculate where it's crossing the x-axis. But I'm going to use this one that we can calculate where it crosses the x-axis first, just so you can kind of confirm what's going on with make sure that this is working for you. All right, so this is what the function of f of x equals x squared minus 2 would look like. I would make an initial guess somewhere like, here's x sub 1, here's x being 1. So I have my function f of x equals x squared minus 2. I need to know what f prime of x is, which is 2x. And a lot of this, I'm not going to show you the calculations. I'm going to have you do it on your calculators. You can kind of pause and calculate it yourselves. But I will go through this. And so then if I want to find, if I know x sub 1 is 1, that was my initial choice there. To calculate x sub 2, I would go to my equation, x sub 1 minus f of x at 1 divided by f prime of x sub 1. And then go ahead and calculate this. So let's calculate it. X sub 2 looks like 1 minus, if I put in 1 into this equation, I get negative 1 divided by 2. Looks like I'm adding those together, so x sub 2 comes out to be 3 over 2, or 1.5. And so then I would move on to my next calculation to find x sub 3. And that one is going to be x sub 2 minus f of x. And so you get, hopefully you get the pattern at this point in time. So I'm going to say 3 halves minus, if I put 3 halves into the original equation, I end up with a quarter, or I'm going to go 0.25. and then we'll divide that by putting it into the derivative, ends up kicking out 3. So x sub 3 will give me a value of 1.417. Well, that's still not close enough to the answer as far as we want to calculate, because we want to calculate to at least 3 decimals. So let's keep going. Let's go one more step, f of x sub 4. And again, I'm going to put it into this equation. I'm just using the x sub 3 values into the equation and going into the original function and into the derivative. So this guy, if I was doing this, it would be x sub 3 minus f of x sub 3 over f prime at x sub 3. So that's what I'm calculating. So x sub 4 will give me, let's say, putting in this value, 1.417, minus substituting in this crazy looking value into my f of x squared minus 2, gave me a value of 0.06944, and then I'm going to divide that by 2.833. And that will then, when I calculate this thing, x sub 4 comes out to be 1.414. Well, that is actually pretty darn close to the actual answer. And like I said, originally you probably wouldn't do this with this type of function, because this function is one we can calculate where it crosses the x-axis fairly easily. Because how do we calculate when we cross the x-axis? Well, we set y equal to 0. So if I set this function 0 equals x squared minus 2, and I start solving, I'm going to add 2 across the equal sign. X squared equals 2. And then if I take the square root of both sides, x will equal plus or minus the square root of 2. But since we started with the x value of 1, well, x equaling the square root of 2, x comes out to be, if I go to a decimal, for the square root of 2, that's basically what we're getting. Now, if we wanted more accuracy, we'd keep going, but that is basically what we get when we take the square root of 2 on our calculator. And so right now, this third iteration is basically close enough for our approximations for this. All right, but if you had one that you couldn't figure out what was going on, this is what you would do. This would be a way to figure it out. All right, so then this one's kind of the same idea, but this time they want an accuracy within this, what is this, tens, hundreds, thousands, 10,000s, 1/10,000th. So the first thing I would do is I would kind of get a graph of what's going on. Since I can't directly find a 0 of this guy, we have -1 here, -2 here. The graph itself does something like this. And so I'm looking for this value, and since I can't calculate it directly, again, if you need to graph this, I would graph this function on my calculator, because you guys have the calculators. But I have to go ahead and pick some value. And looking at this, it looks like -1 would be a good x sub 1 choice. So we'll call that -1. So we have f of x equaling 2x cubed plus x squared minus x plus 1. And then f prime of x, when we take the derivative, gives us 6x squared plus 2x minus 1. And so then I could go ahead and solve this guy going through my iterations over and over again. So we'll start with x sub 2. And x sub 2 would be -1 minus, substituting in -1 into the function. I end up with, into this function, I end up with -1 over 2 when I put in the slope, put it into the slope equation. And when I calculate this value, oops, I did that wrong, sorry. I get +1. Sorry, I calculated that wrong. I put this in, I get +1, and then when I put this into the, when I put -1 into the slope equation, I get 3. All right, so then simplifying that, x sub 2 comes out -1.333 repeating. So then I need a third one. I need a third guess here. So that puts me, if I'm taking my tangent line at 1, I might be, shooting out here somewhere. And so you can kind of see we're going to kind of bounce back and forth on this one. And so then we'll go to x sub 3. X sub 3, if I go ahead and substitute in these values, I'm going to get -1.333 repeating, minus substituting in -1.333 into the f of x function. I would end up with -0.6296. And I'm going to divide that by substituting that value into the slope equation. I got 7. And so calculating that out, x sub 3 came out to be negative 1.24339. All right, so if I want to find the accuracy of these two approximations, well, I would take the sub 2 minus sub 3, and the absolute value of that, and that will then kick out that the accuracy for those guys comes out to be approximately 0.0899. And so if we would have to continue on with this to figure out what's we keep going to this accuracy part of it. So I'm going to go to x sub 4, and x sub 4 is using the x sub 3 value here and substituting it in, and then substituting this value in to f of x. I get negative. Oops, I missed a 0 here. Sorry, I'm trying to read my handwriting here. This is a 0 here, sorry. And then dividing that by 5.78933. And so then if I divide that out, x sub 4, if I can calculate that value, I get negative 1.23386. And so then if I calculate x sub 3 minus x sub 4, substituting those values in, x sub 3 minus x sub 4, I end up with 0.0095. Still not close enough, so I'm going to have to go one more step further and calculate x sub 5. And if I go x sub 5, then I'm using the negative 1.24338. 6. Oops, I got an extra 4 in there. Sorry, I'm having trouble reading my own handwriting here. 2.3386 minus, substituting that value in, I got 5.04533 divided by this one. And so then x sub 5 came out to be negative 1.23375, and if I say x sub 4 minus x sub 5 in absolute values, I ended up with a decimal like this, which unfortunately for us is still not accurate enough. It's close, but we'd have to go one more step, and I'm not going to calculate x sub 6. I will calculate it. I've calculated it, but I'm not going to calculate it for you on the slide here. And so x sub 6 gives me this. And if I do the absolute value of x sub 5 minus x sub 6, then I would end up with this decimal, and this guy is clearly accurate enough for us. I don't know how many zeros I got going on here. It's supposed to be a 0. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. And so this guy is clearly within the range that we'd want to do. So we would need to go to f of 6 or x sub 6 to get far enough into our iterations to figure out the accuracy that they were looking for up here. All right. So then the last thing is, says when does this fail? Well, if the function, if the derivative of the function is 0 at a certain x sub n, then the test will fail. You can't divide by 0. That would make sense. So that would be a problem with this one. Secondly, it will also fail if it's non-differentiable, and that was the whole beginning thing, is that it had to be differentiable. And an example of a non-differentiable function that kind of gives you a shape like this. Basically, non-differentiable is a sharp point. And so that would be an example of that. And then the third time it doesn't work is if the test is divergent, which basically means that as you pick x values, if you're looking at a graph and you got something that looks like this and you pick an x sub 1 here, and then you get x sub 2 there, great, and then x sub 3 ends up out here, and x sub 4 moves out there, and you slowly get further and further away from the actual value that you want, that would be a divergent one, and that's another place this test fails. So we can talk more about this in class. I look forward to talking to you guys about this. So.